Spiders are producing a material stronger than steel using nothing but liquid stored inside their bodies. Somehow, that liquid is transformed into powerful cables engineered by one of nature's smallest builders. Then the spider uses those cables to build giant suspended traps with astonishing mathematical precision. But scientists still don't fully understand how evolution created a biological machine this advanced. We're going to uncover the hidden silk-producing system inside spiders and the engineering process that allows them to build some of the most efficient structures in nature.
This tiny spider can create a material so powerful that it rivals steel in strength. But this remarkable thread is not metal. It begins as a liquid hidden inside the spider. Every strand starts here, inside a hidden biological factory deep within the spider's abdomen. Inside its body, specialized glands manufacture and store the proteins needed to build future silk. Before silk exists, countless protein molecules must first be assembled and carefully concentrated. Over weeks and months, growing spiders develop larger glands capable of producing stronger silk. Everything is now in place. But how did this extraordinary silk system evolve? To understand spider silk, we must travel back hundreds of millions of years. Early ancestors likely produced simple secretions long before true silk ever existed. Over immense timescales, these simple structures evolved into specialized silk-producing organs. Today, each gland functions like a miniature biochemical factory inside the spider. Energy from captured prey is converted into the raw ingredients needed for silk. Thousands of amino acids join together, forming the protein chains that will become silk. The proteins are ready. Next comes the transformation from liquid chemistry into solid silk. Deep inside the abdomen, liquid silk begins its journey through an extraordinary biological production system. Many spiders possess several gland types, each designed to manufacture a different kind of silk. Here, silk proteins are stored at remarkably high concentrations while remaining completely liquid. Each protein folds into precise shapes that determine the silk's future strength and flexibility. Some regions act like microscopic armor, while others provide the flexibility needed to absorb force. Although packed with proteins, the solution still contains large amounts of water. And now, the chemistry begins to change as the liquid enters a narrowing pathway. As the liquid travels forward, the surrounding duct begins changing its chemical environment. The acidity slowly changes, triggering important reactions inside the silk proteins. Proteins that once floated randomly now begin organizing into a common direction. At the same time, water is gradually removed from the developing silk. Removing water allows the protein concentration to rise dramatically inside the duct. New molecular connections begin forming, creating the foundation of future silk strength. The liquid is nearly transformed. Ahead lies the moment when silk becomes a solid fiber. Now the liquid silk reaches the spinneret, the final gateway before becoming a solid thread. The narrowing channel forces billions of proteins into highly organized molecular arrangements. Strong crystalline regions begin forming, creating the microscopic framework responsible for silk strength. Flexible protein regions connect these crystals, allowing silk to stretch without breaking. Instead of concentrating stress in one location, silk distributes force across countless molecules. Within moments, liquid proteins have transformed into one continuous solid fiber. The first thread is born, carrying extraordinary strength within an almost invisible strand. The spider releases a strand into the air, allowing wind to carry it forward. This technique allows spiders to bridge large distances without crossing the gap themselves. When contact occurs, the silk quickly forms a secure anchor point. The spider strengthens the bridge, transforming a single thread into a reliable support cable. From this foundation, the spider begins constructing the web's primary framework. Radial lines spread outward, creating the skeleton that will support the entire web. The first threads are complete. Next comes the engineering that turns them into a functional web. With the main framework complete, the spider begins adding the structures that give the web its shape. First comes a temporary spiral, acting like scaffolding during the construction process. The spacing is remarkably precise, ensuring every future strand is placed correctly. The temporary spiral serves as a guide, helping the spider maintain extraordinary accuracy. Now the spider switches materials, producing the sticky silk used to capture prey. Each new strand carries microscopic droplets designed to trap flying insects. The capture spiral is now forming, transforming the framework into a functional hunting system. What appears simple is actually a highly engineered structure built from specialized materials. Different silk types perform different jobs, just like components inside a suspension bridge. Strong support lines distribute forces throughout the web whenever it experiences stress. Flexibility allows the web to survive impacts that would destroy many rigid materials. When prey collides with the web, sticky spirals absorb energy and prevent escape. The web instantly converts impact energy into vibrations that travel across the structure. The web is more than a trap. It is also a highly sensitive information network. Once complete, the web becomes a living structure, constantly responding to its environment. The spider detects even the smallest disturbance through vibrations carried across the silk network. Specialized sensory hairs translate vibration patterns into precise directional information. When damage occurs, the spider immediately responds by moving toward the affected area. Repair is instant, as new silk bonds restore structural integrity within seconds. At the end of its lifespan, the spider even recycles silk by consuming and reprocessing it. Nothing is wasted. Even destruction becomes the raw material for future webs. Inside every thread lies a hidden world of molecular engineering far beyond human perception. What appears simple is actually one of nature's most advanced engineering systems. If a spider can build such perfection from liquid proteins, what other invisible engineering systems might nature be hiding all around us? Every web is not just a structure, it is a living system of survival, precision, and hidden intelligence. From chaos to structure, and back again. Science continues to reveal the hidden language written inside every strand of silk. The story of silk is not finished. It is still being written in every spider on Earth.